Can you hear me? Hello, can you hear me? Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay. In the last class, we have talked about base classifier, naive base classifier, and then we started likelihood methods. In likelihood methods, we have already discussed one parametric method, which is quadratic discriminant analysis. Okay. So today we are going to see two more parametric models, and then we will talk about one non-parametric model. Okay. So first we will start with linear discriminant analysis. Linear discriminant analysis, or LDA. So here we will discuss linear discriminant analysis as a classifier, not as a data reduction technique. So when we will talk about data reduction technique, then we will consider to have principal component analysis and linear discriminant analysis. So in that way, we are not going to discuss linear discriminant analysis today. So we will discuss linear discriminant analysis as a classifier. Okay. Now this is this is another parametric method. In the last class, when we talk about quadratic discriminant analysis, so we saw that the class boundaries are nothing but the piecewise quadratic function. Okay, so if we consider a 3D model of class densities of three classes of feature vectors, so we can see that the class densities are basically found like this. So this is denoted by, this class density is denoted by A, this is denoted by B, and this class density is denoted by C. Now this is the 3D projection. Now if we get the 2D projection of the same class densities of three classes A, B, C, then we can see, so they might be like, and the separation between the class densities are referred by piecewise quadratic function. So piecewise quadratic function means this is the class boundaries are nothing but the surface between two class A and B, between A and C, between B and C. Okay, so these class boundaries are nothing but the surface are referred by piecewise quadratic in case of quadratic discriminant analysis. But in case of linear discriminant analysis, so we will see that these class boundaries are nothing but the piecewise linear function, not the quadratic function. Okay. Now, for apart from the assumptions which are made for parametric models, so we can have few more assumptions for linear discriminant analysis. So the first assumption in linear discriminant analysis, that here we assume that the covariance matrices of the class densities are equal. Covariance matrices. So In the last class, we have already talked about the model parameters, mean and covariance that we can use in the quadratic model. Okay, quadratic discriminant analysis model. So here also initially we assume that the covariance matrices of the class densities are found to be equal. So this is the first assumption. Okay, now according to this assumption, if I consider there are two classes, then and which is labeled by y, so there will be two classes 0 and 1. Okay, one is negative class, another is positive class. Okay, so according to the first assumption, what we can write? We can write p of probability of y at 1 equals to probability of y at 0 equals to half, or so probability of class density, probability of class density is found to be equal. Okay, so in this case, if we add these two probabilities, we can get 1. Okay, now we are considering that the probability probability of class density for each and every class in the population is found to be equal. Okay, since we are taking two classes 0 and 1, one is negative and positive, another is positive class. So therefore, so each class density, the probability of each class density will be 0.5 or half. Okay, so this is the initial assumption that we make. And as I said, that the estimated class boundaries will be piecewise linear functions. Okay, so here covariance matrix sigma can be estimated from all the data. Okay, all of the data. Data means here the population. Okay, so here we consider the population, and from that population we will estimate the covariance matrix sigma. Okay, now let us consider there are n number of independent draws uh, which are derived from joint distribution xy. Okay, so we can write the independent draws as x1 comma y1, x2 comma y2, and up to we can write xn comma yn. Okay, so these are the independent draws that we can derive from the joint distribution capital X comma y. This is the joint distribution. Okay, this is called the joint distribution. Okay, now so for each class, so here the class small c we can write 1 comma 2 comma capital C. Capital C is the total number of classes. Okay, total number of classes. Now for each class C, so we can get the feature vector as x given y equals to, we can write small c, the normal distribution n of mu c comma sigma. Okay, so this feature vector x when y is given, so is here feature vector x when y is the class level information or class information is given, follows the normal distribution n of mu c comma sigma. Okay, now from here we can determine the mu. So so here we get the mu, which gives us 1 by 1 upon nc. Okay, here we can write I equals to 1 to n xi. Okay, and yi equals to small c. So here nc is the number of training examples in a particular class C. Okay, and here n is the total number of data points in that class C. Okay, and here I equals to, we vary, I equals to 1 to n. So we get the summation over xi for yi equals to c. So yi equals to, for a particular class we get this summation, and this summation, this sum of sum of the data points will be divided by number of training examples which are found in each class. Okay, and this gives us the mean for that particular class C. Okay, similarly we can get the covariance matrix sigma cap. So this is given by 1 by n summation over I equals to 1 to n. We can write xi, so mu cap yi. Okay, and this will be multiplied by transpose of xi minus mu cap yi. We take the transpose. Okay, and so this covariance matrix sigma can be further denoted by summation. Here I equals to 1 to c. Okay, nc divided by n, we can write sigma c. Okay, that means this covariance matrix is determined for a particular class C. Okay, and this can be further derived as the summation over nc by n, which is multiplied by the covariance matrix for a particular class C. Okay, so here we get the summation over all the classes. So summation over this nc by n, which is multiplied by covariance matrix. So for all classes, for all the classes capital C, we can get this summation. Okay, so here we determine the mean and covariance matrix for each class. Then we get the summation over this covariance matrix for C number of classes. Now if mu0 and mu1 belongs to RD, so d-dimensional data. So now we consider that mu0 and mu1 belongs to d-dimensional data, and for sigma, for covariance matrix sigma, so we can estimate the density, which is given by probability of x. So probability x means we can write this also as capital X at point x small x. Okay, given by given the class information y equals to small c. Okay, so this is the estimated density which is given by the probability of small x given by class information c. Okay, so we can write 1 upon 2 pi d by 2 multiplied by sigma, so sigma to the power half. So this is nothing but the equation of Gaussian distribution. Okay, for univariate parameters. So here we can write, so e to the power, so minus half x minus mu c. Okay, and so sigma to the power minus 1, we could write x minus mu c. Okay, so this is the equation for this estimated class density. Okay, so estimated class density, probability of x equals to small x given the class information is is found to be equal to the Gaussian distribution or normal distribution. Okay, so after determining the mean for a particular class and covariance matrix sigma, so we can estimate the class density for a particular class C, small c. Okay, Now, since we need to estimate or we need to determine the model parameters, so here the model parameters are mu and here model parameters are mean and covariance matrix. Okay, so therefore we will go for maximization of function. Okay, maximization of this function. So we will maximize this function. Okay, and upon which we can estimate the model parameters mu and sigma. Okay. So for that we can use the same convention which is used by a base classifier. Okay, so here we can write f cap of x equals to, we can write arg max here c, since we are talking about the two classes, so we can write c belongs to 0 and 1. Okay, and now we are writing probability of y equals to c. So this is nothing but the marginal probability or prior probability, okay, which is multiplied with the likelihood. So we can write capital X equals to small x given by class information small c. Okay. So this function, this function will be maximized so that we can estimate the next probable values for mean and sigma. Okay, mean and covariance matrix. So when f of x is found to be 1, okay, so when the class information is found to be 1, that means when this function, when the class density belongs to a particular class 1, since we are talking about the two classes, one is the negative class 0 and positive class 1. So therefore, after estimating the class density, now we will need to have the class information about that class density that we have estimated. Okay, now when this will be set 1, that means when this estimated density is found to be the positive class. So when the log likelihood ratio, we can write log of probability of 1, probability of x equals to small x given class information, that is the positive class 1, divided by probability of y equals to 0, probability of x equals to small x class information, that is the negative class 0. Okay, and when this log likelihood ratio is found to be greater than 0, okay, then only we can assign the positive class to that particular class density which has been estimated in this equation. Okay, this is the class density, and this will be called log likelihood ratio. Okay, so in terms of log likelihood ratio, we can characterize this class density which has been estimated for a particular class. Since we are talking about the two classes, one is the positive class, another is the negative class. So therefore, we can assign this class density to a positive, or we can have the positive class when the log likelihood ratio is found to be greater than 0. Okay. Now, in our case, the log likelihood ratio becomes, we can write half of x minus mu 0 transpose of x minus mu 0 sigma inverse x minus mu 0. Okay, minus we can write half of x minus mu 1 transpose sigma inverse x minus mu 1. Okay, so in our case this is the log-light ratio. Okay, now if we remember the linear regression equation, that is y equals to mx plus c. Okay, so in this equation, in this linear regression equation, here m and c are the model parameters. Okay, m and c are the model parameters. Now similar to this linear regression convention, we can find another form w comma x plus b. Okay, so this is the comparable form of linear regression equation where w can be determined as mu1 minus mu0 transpose sigma inverse. Okay, so w is given by mu1 minus mu0 transpose multiplied by sigma inverse. Okay, and b is determined as half of mu0 transpose sigma inverse mu0. Okay, and mu1 transpose sigma inverse mu1. So here model parameters w and b are determined from the estimated mu and sigma. Okay, estimated mean and covariance matrix sigma, and then we get this form w comma x plus b. Okay, so here w and b are the model parameters. Now we will talk about the Gaussian mixture model. So whatever we discuss about linear discriminant analysis, so here the linear discriminant analysis is not used as the data reduction technique. So we are using here we are talking about linear discriminant analysis as a classifier. Okay, and this classification is done in terms of the estimated class density. So as I said earlier that the class boundaries are nothing but the piecewise linear function. Okay, so here here the surface that we get between any two class densities are found to be piecewise linear function. Okay, so now you will be talking about the Gaussian mixture model. So Gaussian mixture model is another parametric methods in which we get the maximum likelihood as the class density. Okay, so here we obtain the class densities, then we see the which class estimate the maximum likelihood. Okay, and accordingly we can assign the class information or the class level to that estimated class density. Okay, normally what we know about Gaussian distribution, that in the last two parametric method, in quadratic discriminant analysis and linear discriminant analysis, so we get the Gaussian distribution to estimate the class density for a particular class C. Okay, now here we will take the mixture of such Gaussian distributions. Okay, and this is nothing but the Gaussian mixture models. So for n number of components for a particular class C, so we get this Gaussian mixture models. Okay, now suppose for each class C the likelihood function P of, we can write x equals to small x given the class information C. So this likelihood function, probability of x equals to small x given the class information C is a mixture of Gaussian densities. Okay, now this mixture of Gaussian densities can be represented by summation, yeah, j equals to 1 to jc. Okay, we can write summation over wjc, then we can write this wjc is multiplied with phi of x. This x is the feature vector which is parameterized by mu jc comma sigma jc. So here phi of x, phi of parameterized x is nothing but the equation of Gaussian distribution. So this represents the Gaussian distribution. Okay, now we get the summation over wjc which is multiplied by phi of x, parameterized by mean and covariance matrix sigma. Okay, now as I said, the phi of x parameterized by mean and covariance matrix sigma, which is nothing but the Gaussian density function, and wjc is the non-negative weights, non-negative with a particular class C. Okay, so this non-negative weights, non-negative weight is determined for the determined for j number of components. Okay, so within a particular class we get this j number of components, and summation of this j number of components is referred by wjc. Okay, so we can write w1c plus w2c plus wjc. So this will give us 1. That means the summation of these weight components are found to be 1. Okay, so for that particular class C, we get these weight components from w1 to wj. Okay, and we take the summation over these weight components which is multiplied by Gaussian density function phi of x parameterized by mean and covariance matrix sigma. Okay, now here jc greater than 0. So here jc is the mixture component for a particular class C. This is called the mixture component. Mixture component. Okay. Next we will see. Next we will see the log likelihood of an observation x. So that can be given by the log of the Gaussian likelihood estimation. Okay, so here we can have can you hear me?
Yes, sir.
Yes, sir.
Okay, okay. So the number of mixture component JC is determined for each class using a model selection criterion. Okay, so we will talk about the model selection criterion in the subsequent class, but for the sake of the discussion of Gaussian mixture model, so this is sufficient to know that the model selection criterion give us the mixture component JC. Okay, now let us consider theta is the parameter of the joint distribution x and y. So here we could write theta equals to so theta consists of 3 model parameters. One is the weight wj, mean mu jc, and covariance matrix sigma jc. Okay, for a particular class C. So we can write theta equals to WJC, comma, mu JC, comma, sigma JC. Okay. So this since we are not writing these model parameters, three model parameters independently, but we are taking another parameter theta, so which consists of these three model parameters. Okay. Now the log likelihood, if we consider an observation small x, then for this observation, so we can estimate the log likelihood. Okay. So how this log likelihood will be given? So we can write log of p theta capital X equals to small x. Okay. So this is the log likelihood of the log likelihood for a given observation x. So we can write, so this is given by log of, now we will write summation over p theta capital X equals to small x. Okay. So this p theta x equals to x, small x, comma, y equals to c. So this is nothing but the joint distribution. Okay. Now in place of joint distribution, so this joint distribution, the summation, here we are taking the log of summation over this joint distribution, which is parameterized by theta. Okay. And theta consists of these three model parameters: weight, mean, and covariance matrix. Okay. Now we are taking the uh, log likelihood of the given observation x. Now we are again we are considering s equals to x1, x2 up to xm. Okay. So this s is nothing but the independent and identically distributed sample. Okay. And here we would like to find the theta that maximizes the log likelihood of s. Okay. That maximizes the log likelihood of f. So here the log likelihood that we have estimated from this derivation, log of summation over j equals to 1 to jc, this summation is estimated over the joint distribution p theta of x equals to x, comma, y equals to c. Okay. Now again we are considering that there is an independent and identically distributed sample s, which is given by x1, x2, and up to xm. Okay. Now we would like to find the theta that maximize the log likelihood of s. That means since we are interested to have the maximum likelihood of any class of feature vectors, so therefore after maximizing this function, the log likelihood function, so we can estimate the model parameters theta. Okay. And by which we can get the maximum likelihood of a class of feature vectors. So for that we could write L of theta, which is given by log of I equals to 1 to m. So this log of product over p theta x equals to x, small x. Okay. And in place of, so in place of the, what we can write, we can write I equals to 1 to m, since here we are considering a sample space S, which is given by m number of data points. Okay. So therefore we could write log of p theta x equals to small x. Okay. And further we can write summation, so I equals to 1 to m summation over log of j equals to 1 to jc, summation over p theta, so summation over this joint distribution. How can we interpret this relation between L theta and the right hand side? So here in the right hand side, when we further derives the log likelihood function. So in place of log likelihood, we are writing the joint probability distribution p theta of x equals to xi, p theta of x equals to xi, comma y equals to c. That means for a particular class C, we get the summation. We get the summation over this joint distribution. Okay, joint distribution p theta, and further we get the summation over this m number of data points which are given in the sample space S. Okay, now since we are interested to have this interested to find the theta that will maximize the log likelihood function for observation S or sample space S, so therefore for each and every class we need to get this summation of this joint probability distribution. Okay, that means for each component we estimate this for each weight component we estimate the joint probability distribution, then we take the log of this joint probability distribution, and after taking the log of the over joint probability distribution, further we get the summation over m number of data points. Okay. Now from here, how can we get the maximum likelihood estimator, which is the solution of the maximization problem? Okay, so therefore here we can write arg max. So here we are interested to maximize the function. So previously in the base classifier and naive base classifier, we were interested to have the minimize the function. Okay, now here we are interested to maximize the function, since we need to estimate the maximum likelihood of a class of feature vector. Okay, so therefore we need to maximize the log likelihood function. So we can write argmax for theta, L of theta, which is given by argmax theta y equals to 1 to m log of, we will write the same derivation that we have obtained in the previous step. Okay, so summation over j equals to 1 to jc joint distribution, which is parameterized by theta. So x equals to xi, comma y equals to c. Okay, so we know how to minimize a function, how to maximize a function. So similar convention we will use here, and we will apply here, and to get the maximization of function L theta. Okay, so L theta is nothing but the log likelihood function. So till now we have discussed about the parametric models of likelihood methods. Now we will be start talking about the non-parametric methods. Okay, so one such non-parametric method is kernel density estimation. So kernel density estimation. So for parametric method, we have made few assumptions like the population that we are studying follows the normal distribution, okay, or Gaussian distribution. So in terms of mean and covariance matrix, we estimate the class density. But in case of non-parametric method, we are not considering the normal distribution, and we are not estimating the class density in terms of mean and covariance matrix. Okay, and here the number of parameters are not fixed. So these two aspects separate the non-parametric method from parametric method. Okay, so here we are not making any assumptions in non-parametric method. One such non-parametric method is kernel density estimation. So here the kernel density estimation estimates the density function that produces a sample of data. Okay, now how this sample of data is produced? So the sample of data is produced by placing a probability mass. Okay, probability mass at each observed datum or each observed datum xi. Okay, and also we can place this probability mass nearby each observed datum or xi. Okay, now when we estimate the class density using kernel density estimation, then we have to make few assumptions apart from we have to make few assumptions, or we will see some observations that will comply the non-parametric methods. Okay, or the conditions to be to have the non-parametric method. So how this kernel density estimation works? So kernel density, basically there will be a population. Okay, so with that population, what we do with kernel density estimation, we plot out the data. Okay, and we can start to create the curve of distribution. Curve of distribution means the distribution of data, and this distribution is data is referred by the population. Okay, and here we are interested to have the plot out of the data, and we can start to create a curve of this distribution. Okay, and the curve is calculated by weighting the distance of all the data points, in each specific location along the distribution. Now for a particular distribution of kernel density estimation, so we get the weighting we get the curve which is calculated by weighting the distance of all the data points. Okay, and along the distribution. So here the kernel function is the specific mechanism that to be used to weight the point across the data set. Okay, data set here means the population. Okay, now let us let us try to understand the kernel density estimation further, and we will see how this kernel density estimation can be used to estimate the class density without using the normal distribution parameters. Now the class density estimation is given by p cap of x given class information y equals to c. Okay, so here the kernel density estimation is estimated for a particular observation small x. Okay, and since this is the equation of the likelihood function, so we can write the probability of x given class information y. Okay, y equals to c. So this likelihood function is given by 1 upon nc summation over here I equals to 1 to n for n number of data points, and here we can write 1 upon h to the power mc. Okay, h to the power mc. So m is the total number of data points, and c is a particular class for which we are interested to have the kernel density estimation or class density. So 1 upon HCM is multiplied by capital K of x minus xi by HC. Okay. So here capital K is nothing but, we can write capital K such that the sample space tilted x 0 comma infinity. So here you can see that first when we write this representation, first we write the third bracket, then we write 0 comma infinity, then we write infinity symbol, and it is closed by the first bracket. Okay, so in the same range we are using the third bracket and first bracket. What does this mean? The first bracket, the third bracket, so this range start from the third bracket. That means we start at 0. Okay, so one endpoint is 0. So we start at 0, but we don't know the endpoint. So therefore, that is why we are writing, after writing this infinite symbol, we are making this first bracket, which is closed by this range. Okay. So here the capital K is the kernel function. Capital K is the kernel function, and HC is known as the bandwidth. Okay, so this in this equation, kernel density estimation equation, HC is very important. Okay, so particular class we get this bandwidth, and this bandwidth controls the shape of this kernel density estimation. That means the class density that we are that we are estimating for a in the given population. So this HC, this parameter, this bandwidth parameter controls the shape of this class density. Okay, now suppose there is a population and we get the curve of density in the given population, and to using this bandwidth we can smooth the curve of this distribution or curve of this class density. Okay, so that is why this bandwidth parameter is known as the controlling the shape parameters, or controlling the shape of the class density, which is estimated by kernel density estimation. Okay, so here capital K is the kernel function. So here you will see the kernel function when we will be talking about neural networks, when we will be talking about support vector machines. So there we will study the kernel functions in different way, and we will try to learn how the kernel function works in a class density estimation. Okay, so apart from these kernel functions, here we are having another parameter, bandwidth parameter, which controls the shape of the class density. That means the shape of the curve which is plotted for a particular distribution in the population or in the data set. Now sometimes we use this kernel density estimation to get the smooth curve of the distribution or class distribution in a population, and therefore when we get the bandwidth value low, then we can get the congested points, and for that congested point, so we get the class density function, so which is not the smooth function. Okay, or a smooth curve for a distribution. So therefore to get the smooth curve, this bandwidth is very important in kernel density estimation. As I said earlier that this kernel density estimation works by plotting out the data, and we can start to create a curve of the distribution. Okay, and this kernel function is used to weight the point across the data set or across the population. So these two parameters are important, and depending upon these two parameters we can decide the smoothness of the curve for a particular distribution. If you have any questions, you can ask me. Otherwise, we will stop now. Any questions? Okay. So that's all for today.